Welcome back to Examify's IGCSE Physics course. Now we are on Unit 3, Waves. In this unit, we are going to explore one of the most fascinating ways energy travels in our world, through waves. From the sound of your favorite song to the light from the sun, and even the signals that you make your Wi-Fi work, it's all waves. You will discover how waves move, how they reflect, bend, spread, and how we use them in technology, communication, medicine, and everyday life. We will start by understanding the basic properties of waves, then dive into light, sound, and the entire electromagnetic spectrum. By the end of this unit, you won't just know what waves are, you will see them everywhere around you. So get ready. This is where physics starts to feel like magic you can explain. Today we are starting Unit 3, and the first thing we need to know is, what exactly is a wave? A wave is simply a way of transferring energy from one place to another, without any transfer of matter. That means the particles themselves don't travel with the wave. They just oscillate or vibrate about their rest position while the energy moves forward. There are two main types of waves, transverse and longitudinal. In a transverse wave, the particles vibrate perpendicular to the direction the wave travels. Imagine moving a rope up and down while the wave moves forward. That's perpendicular motion. Auto waves, light waves, and seismic S waves are examples. In a longitudinal wave, the particles vibrate parallel to the direction the wave travels. Here, the particles bunch together and spread apart in the same direction as the energy. Sound waves and seismic P waves are examples. And now, I'm going to give you a quick physics hack to remember the seismic S waves and seismic P waves. As you can see, in seismic S waves there is an S, and in transverse there is an S. So always remember that seismic S waves are a transverse wave, and the seismic P waves are the opposite, as in they are the longitudinal wave. And now, let's break down the main features you need to remember about waves. First is the amplitude. Amplitude is the maximum displacement from the rest position. Bigger the amplitude means more energy. Second is the wavelength. Wavelength is the distance between two identical points on consecutive waves, such as crest to crest or trough to trough. Frequency. Frequency is the number of complete waves passing a point each second. It is often measured in hertz. The fourth one is the crest. Crest is the highest point of a transverse wave. Fifth is the trough. Trough is the lowest point of a transverse wave. Sixth is a wavefront. Wavefront is an imaginary surface connecting points that are in phase, which means that their vibration is in the same way at the same time. Last one is the rays. Rays are arrows showing the direction of wave travel, always perpendicular to the wavefront. Next up, we have wave speed. Wave speed is the speed at which a wave travels. The formula to calculate wave speed is v equals f times lambda, where v is the wave speed, f is the frequency, and lambda is the wavelength. This formula applies to all waves, whether they are sound, water, or light. You might have already known that waves can reflect, meaning they bounce back after hitting a surface. The law of reflection says the angle of incidence equals to the angle of reflection. The incident ray, the reflected ray, and the normal all lie in the same plane. Next up, we have refraction. Refraction is the bending of a wave as it changes speed when entering a different medium. If the wave enters at an angle, its direction changes, except if it travels along the normal, where it just changes speed without bending. That is, when the wave is traveling along the normal, there is no refraction taking place. The last behavior of a wave is diffraction. Diffraction is the spreading out of waves when they pass through a gap or an obstacle. Through a gap, more diffraction happens if the wavelength is similar to or larger than the gap width. When around the edge, more diffraction happens if the wavelength is longer. This is why you can hear someone talking around the corner even if you can't see them. Welcome back, and now we are going to jump into light. First up, we have what is the nature of light. So light is a type of electromagnetic wave. That means it doesn't need particles to travel. It can move through a vacuum like the space between the earth and the sun. Light waves are transverse, so the vibrations are perpendicular to the direction of the travel. Now we move on to the reflection of light waves. Light obeys the law of reflection, that is, the angle of incidence equals to the angle of reflection, and the incident ray, reflected ray, and the normal all lie the same way. Mirrors produce clear reflections because they have smooth surfaces, so reflected rays stay parallel. Talking about reflection of light, we need to consider the reflection by the plane mirror. Some of the characteristics of images formed by the plane mirror are: it is the same size as the object, the image is at the same distance as the object from the mirror, the image is laterally inverted, and it forms a virtual image. Moving on to refraction of light. Refraction happens when light changes direction while moving from one medium to another. For example, from air to glass or glass to water. This happens because light changes speeds in different materials. If it slows down, it bends towards the normal. If it speeds up, it bends away from the normal. One of the most important concepts when talking about refraction in light is called the refractive index. The refractive index, denoted by the symbol n, tells us how much the light bends. This refractive index can be calculated with the formula n equals sin I over sin r, where I is the angle of incidence and r is the angle of refraction. For light going from air to into another medium, you can also use the formula n equals speed of light in air divided by the speed of light in medium. One more concept to remember is the critical angle and the effect of total internal reflection. The critical angle is the smallest angle of incidence in a dense medium at which the light is totally reflected back inside. If the angle of incidence is greater than the critical angle, total internal reflection occurs. Light doesn't leave the medium at all. This is used in optical fibers for high-speed internet and in medical endoscopes. The next concept we will be looking into are thin lenses. There are two types of lenses, namely the converging lens and the diverging lens. Converging lens bends light rays towards the focal point, and diverging lens bends light rays away from the focal point. Now you might be asking, what actually is a focal point? So there are two important terms you need to remember here: the focal length and the focal point, also known as the principal focus. The focal length is the distance between the center of the lens and the focal point. The focal point is a point on the principal axis where parallel light rays meet after passing through the lens. As a part of IGCSE physics syllabus, we will only be considering the characteristics of image found via converging lens. If the object is close to the lens but away from the focal point, the image will be real, inverted, enlarged. The application of this kind of a lens is a projector. If the object is far away from the lens, that is, it is more than twice the focal length, then the image will be real, inverted, and diminished. An application of this is the camera. This is used to focus the image on the lens of the camera. Moving on, we have a very special type of lens known as the magnifying glass. This occurs when the object is between the focal point and the lens. So the image formed by this kind of lens is virtual, upright, and enlarged. Next up, we have the effect of long-sightedness and short-sightedness and the use of lenses to correct the vision. Short-sightedness is a phenomena where you cannot see far objects clearly because the eye lenses focus light in front of the retina. The solution to this is using a diverging lens to focus the light on the retina by increasing the focal length. Next is the long-sightedness. Long-sightedness occurs when you cannot see closer objects clearly because eye lens focuses light behind the retina. The solution to this is the converging lens. This helps to focus the light on the retina by decreasing the focal length. White light is actually a mixture of colors. When it passes through a prism, it splits into a spectrum because different colors bend by different amounts. Red light bends the least and violet bends the most. This is why rainbows form. Welcome to Chapter 13, Sound. In this chapter, we are going to explore one of the most familiar and important types of waves in your life. From your alarm clock in the morning to the conversations you have during the day, the music you listen to it at night. Sound is everywhere. But what is sound really? How does it travel from one place to another? Why does it sound different underwater or through walls or in a big empty room? We will look at how sound is made, how it moves, how fast it can travel, and how we can measure it and use it in technology, from medical scans to underwater exploration. So get your ears ready, because we are about to turn up the volume on your understanding of sound. Sound is a type of longitudinal wave generated by vibrating objects. When an object vibrates, it creates disturbances in its surrounding medium, resulting in regions of compression where particles are closer together and rarefaction where particles are spread further apart. These fluctuations in air pressure are what your ears pick up as sound. Importantly, sound requires a medium, be it air, liquid, or solid, since it relies on particles to transmit vibration. Consequently, sound cannot travel through a vacuum when there are no particles to carry the wave. The speed at which sound travels varies significantly depending on the medium. In air at room temperature, sound travels at around 340 meters per second. In liquids, such as water, the speed of sound increases to approximately 1480 meters per second, or 1500 meters per second. For solids, sound travels even faster, with speeds reaching up to 6000 meters per second in materials like steel. This increase in speed occurs because the particles of solids are densely packed, facilitating quicker transmission of the vibrations compared to gases and liquids. We have three experiments in the IGCSE physics syllabus to determine the speed of sound. The first one is the non-echo method. The steps here are: there will be two people standing at a large distance from each other. Measure the distance between them using a measuring tape. Record the distance D. Give one person a starting pistol and another person a stopwatch. When person A fires the pistol, B starts the stopwatch as he sees the flash. Note that we assume the flash can be seen instantaneously. After a short time, B stops the stopwatch when they hear the sound. Record the time t. Then calculate the speed of the sound using V equals S over t, where V is the speed, S is the distance, and t is the time taken. The second method to determine the speed of sound is the oscilloscope method. An oscilloscope is a machine that shows graphical representation of the frequency of the sound. Here, there will be two microphones placed at a few meters away. The oscilloscope can then read the recordings when you speak into one of the microphones and receive at the other end. The graph and the distance can be used to then calculate the speed of sound using the same formula, V equals S over T. Moving on to some properties of sound. There are three properties you need to remember for the IGCSE syllabus. First is the pitch. Pitch is a characteristic of sound that correlates with its frequency, expressed in hertz. A higher frequency results in a higher pitch, which is perceived as a distinct note or tone. Second is the loudness. Loudness relates to the amplitude of the sound wave. A greater amplitude results in a louder sound, while a smaller amplitude leads to a softer sound. Loudness is typically measured in decibels. The last one is the quality, or the timbre of sound. This refers to the unique tonal characteristics that distinguishes different sounds, even when they have the same pitch and loudness. This is determined by the waveform shape, which comprises various harmonics and overtones. And that's why different instruments have different tonal characteristics. The human hearing range typically spans from 20 Hz to 20 kHz. Sound that exceeds the upper threshold are classified as ultrasound, while those below the lower threshold fall into the category of infrasound. Ultrasound technology finds practical applications on various fields, including medical imaging like fetal ultrasound and the cleaning of delicate objects due to its ability to generate high-frequency sound waves that produce strong pressure vibrations. Infrasound is often associated with natural phenomena such as earthquakes, volcanic eruptions, and even some animal communications. The last and by far the most effective method for measuring the speed of sound is by utilizing echoes. To perform this, you emit a sound towards a solid surface, like a wall, and measure the elapsed time it takes for the sound to travel to the wall and back. The total distance traveled is then twice the distance to the wall, allowing you to calculate the speed of sound by dividing the total distance by the time taken for the sound to complete its journey. Welcome to Chapter 14, the Electromagnetic Spectrum. In this chapter, we are going beyond what our eyes can see and exploring the full family of the electromagnetic waves, from giant radio waves to tiny, powerful gamma rays. You will discover how all these waves travel at the same speed in a vacuum, but differ in their wavelength, frequency, and energy. We will look at how they are used in everyday life, from Wi-Fi signals and microwave ovens to X-ray machines and cancer treatment, and the dangers they can pose if you are not careful. By the end, you will realize that the visible light we see is just a tiny slice of the spectrum, and there's a whole hidden world of waves buzzing around us all the time. So let's switch on our scientific curiosity and dive into the spectrum. The electromagnetic spectrum encompasses all types of electromagnetic waves, which are organized according to their wavelengths and frequencies. Key characteristics of the electromagnetic waves are uniform speed. All EM waves travel at the same speed in a vacuum, approximately 3 times 10 to the power 8 meters per second, which is the speed of light. And the wave type. All electromagnetic waves are classified as transverse waves. This means their oscillations occur perpendicular to the direction of the wave propagation. Lastly, the energy transfer. Electromagnetic waves can transfer energy through space without the need of medium, allowing them to travel through a vacuum of space. The order of the electromagnetic spectrum from longest wavelength to the shortest are as follows. First comes the radio waves, then microwaves, then infrared radiation, visible light, ultraviolet radiation, X-rays, and lastly the gamma rays. Here's a memory trick you can use to remember the electromagnetic spectrum. Raging Martians invade Venus using X-ray guns. Now let's move on to some uses and dangers of the electromagnetic waves. First comes the radio waves. Some of the uses of radio waves are they are utilized in broadcasting audio and video signals, as well as communication technologies like Wi-Fi and cell phones. The Bluetooth on your smartphone also uses the radio waves. Now the dangers. They are generally safe at low intensities, but can lead to exposure concerns at very high levels, potentially causing tissue heating or other health effects. Moving on to microwaves. The uses are they are commonly used in microwave ovens for cooking food, and then satellite communications for transmitting data signals. The dangers that can be caused are the internal heating of tissues, and exposure to high levels may lead to burns or other health risks. The infrared radiation. The uses include they are employed in heating devices, remote controls, and night vision equipment for improved visibility in dark conditions. Excessive exposure to infrared radiation can lead to skin burns and heat-related injuries. Moving on, let's look at the uses of microwaves in telecommunication. There are two types of artificial satellites that we use. One is the low orbit satellite, and the other is the geostationary satellite. The low orbit satellite orbits around the Earth for satellite phones. The geostationary satellite orbits the Earth and stays in the same position relative to the planet, since it orbits at the same speed as the Earth's rotation. This is used in satellite TV. Mobile phones and wireless internet uses microwaves because microwaves can penetrate some walls and only require a short area for transmission and reception. Bluetooth, as we talked before, uses radio waves because radio waves pass through walls, but the signal is weakened on doing so. Optical fibers are used for cable television and high-speed broadband because glass is transparent to visible light and some infrared. Visible light and short wavelength infrared can carry high rates of data. The last topic in this chapter, and potentially the whole unit, are the signal types. There are two types of signals, digital and analog. Digital signals are the ones that have two values, high or low, or in computers they are represented by ones and zeros. Analog signals are the ones that can be any value within a certain range, and they can be varied. The advantages of digital signals over analog when transmitting data include the increased rate of transmission, the increased range of the data, and that the digital signals are not affected by the noise and can be regenerated easily. And that's the wrap for Unit 3, Waves. We have explored how waves carry energy without carrying matter, learned the differences between transverse and longitudinal waves, and discovered how light, sound, and the electromagnetic spectrum shape our everyday life. You now know how to describe, measure, and calculate wave properties, and you have seen how reflection, refraction, diffraction, and even total internal reflection play a role in technology, nature, and science. Most importantly, you have gained a new lens for looking at the world, because whether it's the color of the sunset, the echo in a canyon, and the Wi-Fi that streams your favorite video, waves are everywhere. Keep practicing, keep asking questions, and remember, the more you understand waves, the more connected you are to the invisible patterns that power our universe. So, fantastic work! And now, get ready, because the next unit will take your physics journey even further.